This video focuses on the input control plane and reports examples of the behavior of the real-time and long-term algorithms that have been included in the final demonstrator. The control plane processes are provided by the NSOS, which stands for Network and Service Operating System, and by the NSMAN, the Network and Service Management. In the input demonstrator, the NSOS and the NSMAN functionalities have been integrated in the European Volcano StratoV module and in the Ericsson Network Manager, respectively. The NSOS is responsible for the real-time configuration of the infrastructure, the dynamic instantiation and migration of personal cloud services, and it includes the consolidation and orchestration criteria. The key performance indicators monitored by the NSOS are used by the NSMAN to perform data analytics and provide trend estimates to decide on the long-term configuration of the underlying infrastructure. The algorithm used for the NSMAN for KPI prediction is based on a multi-seasonal multiplicative model. In our case, forecasts are determined for the aggregated usage of CPU and RAM of each data center, and weights are assigned accordingly. We have used traffic traces from Yahoo and the Hibernia global topology as reference for this demonstration. This network is composed of 55 nodes, which we distributed into 20 data centers, 17 interconnection switches, and 18 access switches. Each data center contains 20, 50, or 100 servers. The network visualization provided by the INAM web interface includes a number of charts to characterize the current load of the data centers and the management weight computed over a time window of 1 hour. In the center of the web page, we can see the network topology composed of data centers and switches. Each data center can be expanded to show its servers. On the top right, a bar chart reports the weights computed for each data center. The network tree on the left allows selecting the data center to be shown in the bottom center graph. Such graph alternates between the view of the CPU and memory load. In both cases, the graph reports two lines. One plots the real values measured in the previous 24 hours, and the other plots a prediction based on the previous 3 days. The weights in the bar chart are an average of the values computed for the CPU and the memory. Data center 13 has been selected from the network tree to be shown in the graphs. It can be noticed that the load values correspond to the ones plotted in the Open Volcano web interface. Such interface shows data centers 4, 8, and 13, and reports the values of the CPU and memory load and CPU and memory weights. Data center 8 is now selected for visualization. As noted before, the graph view alternates between the CPU and the memory load. The radar diagram on the bottom right cyclically reports the current and estimated values of CPU and memory for all data centers over 24 hours. The buttons below the bar chart on the right allow us to select the data centers whose weights we want to visualize. The panels on the right can be closed to leave more room for the graphs and the network topology. The weights provided by DNM as shown in the beginning of the video are used to compute user profiles, which allow the NSOS to operate in a more timely fashion. As an example of user profile, we show now what happens when two users subscribed to the same personal services are characterized by different mobility indexes. Two users are placed in the same data center with the related centers. When the users start moving within the network, the service instances of the red user are more likely to be migrated with respect to those of the yellow user. As a matter of fact, the higher migration frequency of the centers belonging to the red user is driven by the mobility index, which is an example of the user profiles that have been developed within input. The presence of a separate manager with long-term analytics capabilities allows the NSOS to handle the real-time aspects of the service placement by means of lightweight algorithms. We propose an example to show the behavior of the consolidation strategy we have designed for the demonstrator. In order to show how the initial placement can affect the consolidation performance, we consider a situation in which the initial placement is far from optimal, as can be inferred by the reserved CPUs chart in the bottom left corner. In this case of a suboptimal initial placement, and since the algorithm is constrained by performance requirements, 3 consecutive steps are needed to obtain the final consolidation, which corresponds to occupying 58% of the active servers. Instead, in the second case, the initial placement distributes the virtual machines in a more uniform fashion. It is worth noting that the final obtained configuration is the same. However, in the presence of better initial conditions, it only takes one consolidation step.